to give me Vk, and finally give my F, and that F is small. But when I have a freedom of choose that, but sometimes I don't, sometimes I do. All right. So in here I see the arbitrary vector. And how can I get an arbitrary vector? And now how can I determine this arbitrary vector such that I can have a small f? All right. So that is Vk, V0k, Ck. All right. And that's what I got. All right. But my Vk, that inside that Vk, I have my psi k and f psi k. Okay. That's my Vk. If you look at my screen here, Vk has two parts. The first part is n by 1, and the second part is the r by well, this is r by 1, but I need to explain this one now. Okay. Now, this Vk is n by 1 vector, and f Vk, that's the n by 1. That's the then that's the r by n. So Vk is r by 1 vector. R means the number of inputs. That's number of inputs. All right. And that is in here, define that here. And so you look at that definition there. Then the FCK, that FCK Vk bar equal to Vk hat. So this one here, I divide that to be let me rewrite this. This, assume I compute this by that, and this I make them to be two piece. Sorry, need to be notation is not right. Two piece. That two piece, and this, the first piece n by 1, the second piece r by 1. And that, in theory, that's my psi k, and that's my fc psi k. So, this is n by 1, and this is r by 1. As soon as we determine Ck, then we can make this Vk bar equal to my cross loop eigenvectors, and then I can make Fc k equal to Vk hat. Okay. Now this one determine cross loop eigenvector. All right, and hopefully the second one, the second equation will give us f. So if we do this, the k, so we have our n eigenvalue. If AC is n by n, then we have n eigenvalue. So we have n eigenvalues. We have total n equations for that. All right, the n. So again, we can see this. Again, every time I get a head here, and they give me problem. So I think your amount is correct, right? So this is going to be head. This is going to be head. All right. Let me see what happens. Okay. All right. Let me see. All right. We can erase this guy. This guy. Okay. So we have the total of n eigenvalues. So we have total of n cross eigenvectors. Then if this is n by n, this is r by n, so f, then f will be simply just this inverse, this Stark's equation here, and again, sorry about the software here, this head, and this head. So I can solve this f. So that's my gain, my f gain. That's my cost of gain. And now you got to be careful here. I have to explain to you a little bit more here. Now, you know that the gamma k, that's the AC minus standard Ki and BC, right? Well, careful about this, because in general, the lambda k is a complex number. It's complex variable or complex value. So this gamma k is a complex, this complex matrix. That means all this is complex. Okay. All this is complex. All this, oh, sorry. It's not good. All that is complex. So FC equal to now 3-1 hat, 3-2 hat, and 3n hat times 3 bar 1, 3-2 bar, and 3n bar inverse. And this is all complex. And this is all complex. That has to be real. So how can I do that? We have complex matrix here, and the result has to be real because the force is real. The force cannot be complex. And what happened here? Well, it's so when you have a desired eigenvalue, this desired eigenvalue, the desired eigenvalue now, that desired eigenvalue, if lambda k is my desired eigenvalue, and then lambda k conjugate is also my desired eigenvalue. I have to make sure about that. Okay? So, that means that if lambda 1 is complex, lambda 2 will be lambda 1 conjugate. Okay. All right. Then lambda 3 and lambda 4 will be lambda 3 conjugate. The real doesn't count. However, the desired eigenvalue, you cannot have a complex desired eigenvalue alone, because that has to be complex and conjugate, so that when you compute the whole matrix out, this has to be complex, a complex conjugate of that one, and so on. The same thing, this complex, then this has to be complex conjugate of that one. If you make sure that is the case, then this will be real. All right? Constant eigenvalues cannot have a complex alone without its complex conjugate in that closed loop system. That's because that has to be real. If you have a complex gain in your closed loop system, you can implement it. All right? You cannot say, oh, I get a complex of this, I just choose the real one. No. So when you compute this, coming out and you find out you have a complex FC, that means something wrong in your design. Okay. Now here is another important things here is for now we like this to be what? As small as possible, right? What do we mean a small matrix? Huh? If this is the matrix, what do we mean is small? Yeah. What do we mean is small? Well, you can define yourself. The norm is small, right? Or every element is small, depending on how you define it. Now, if we wanted this as small as possible, this guy has to be invertible, right? If this guy is not invertible, that means that is FC will be very large. If this is a, you have to make sure about that. Now, you might say, okay, if this is not invertible, can I make pseudo inverse? The answer is no. But when you design when you